So last time we introduced block ciphers as one of the main atomic primitives, one of the building blocks and starting points for the higher level schemes we want to arrive at. And recall that a block cipher is a two-argument function like this. Its first input is called a key, drawn from a space called keys, and its second input is from a set D, and its last input is from a set R that is in fact equal to D when it's a block cipher. We view this function as entirely known and public, meaning its description is available to anyone, including the adversary. Now, we studied DES as a particular design, and by studied, it just means that we described how it worked and a little bit of its history. Perhaps there was not a lot of understanding as to what security it provides or why certain choices were made. And indeed, much of it will remain a mystery in that sense, part of what makes it intriguing. But nonetheless, we do want to understand as best possible what security it provides so that we can use it better as a building block and obtain effective security out of it. When we ask the question of what security it provides, we go back to that first and important element, which is we first need to say what we mean by security, and we want to get a definition of it. And it should be, in fact, quite precise and mathematical so that we can assess whether things meet it or not. So let's present the first and probably most basic such security goal or definition, the one, in fact, that cryptanalysts most commonly like to target and talk about. And it'll be described as a game, and the game is closely modeled on the sort of example usage case that we saw earlier. So we assume that, again, this block cipher itself is a known public entity. Nothing so far is secret. But now the sender and receiver Alice and Bob share a target key. That means a key has been drawn from the key space at random, and we call it the target key because it's the adversary's target. Alice will start encrypting messages. Each message is just a point in the domain of the block cipher in this set D. By applying the block cipher with this target key K to get an output ciphertext C sub I, and she then transmits all the ciphertext to Bob, and will let Q, a parameter of this definition, be the number of messages encrypted. The adversary is on the line, so we assume it gets all these ciphertexts. It wasn't given the key, of course. Now, we'll also assume it actually knows the messages. This may seem a bit mysterious at first, so we'll discuss it later. What is it the adversary wants to do? It wants to figure out this target key. Its job is to find out what key Alice and Bob were actually using, because once it has that, it has complete decryption capability. It could take any ciphertext that Alice sent in the future and decrypt it because it has the key by applying the block cipher inverse function in the same way that Bob, the receiver, would and just get back the message. Cryptanalysts are particularly concerned about this key recovery security because it's a devastating security vulnerability. An adversary in possession of the key effectively can decrypt everything and you have no security left. So our first target would be to be concerned with its ability to recover the key. However, one of the important skills or angles of approach we'll learn in the class is to be critical about these metrics of security. Already here we can start asking ourselves questions. For example, why does this definition assume the adversary knows the messages? Of course it knows the ciphertext because it's eavesdropping on the line. But the whole point of encryption is to protect the messages. Here I'm saying I'm giving them to the adversary, so then it has nothing left to do. What's going on here? What this is trying to capture is a kind of worst case scenario. It's wrong to assume that the adversary knows nothing about data There are many reasons why it might find out something. One of them is that what we call a posteriori revelation. What that means is that at the time encryption was performed and the ciphertext was sent, the adversary didn't know the data. But later it figured it out. Why? Because actions were taken based on the data. For example, the data may have been, let's have a meeting tomorrow at 10 a.m. The adversary didn't know that, but it was an important meeting, and after the meeting took place, everyone knows it took place at 10 a.m. So now the adversary knows what the message was. And things like this mean it's a good idea to think that the adversary has quite a bit of information about the data and that the real target is the key. A second reason is simply that we are conservative. If we can obtain security even when the adversary knows the messages, we have a better guarantee than if we can obtain security assuming it doesn't know the messages. And so we target the more stringent goal. Now, as we approach defining this, we'll see that there are more fine-grained distinctions, and there are actually two possible metrics of security. We'll call one target key recovery and the other one consistent key recovery. We will be giving these in terms of what we call games, and this will be an introduction to using games as a way to specify definitions and to associate to an adversary something called its advantage, a number determined by the game and the adversary. The game is effectively an environment which functions as what the adversary is attacking and determines how and when the adversary is successful. Now, it turns out that this will allow us to define target and key recovery, consistent key recovery security for any family of functions, not just a block cipher. Remember, a family of functions is a superset of the set of block ciphers. The set of families of functions is a superset, meaning all block ciphers, any block cipher is a family of functions, but not vice versa. In other words, this definition will apply even when the individual functions determined by a key are not permutations. In terms of terminology and also in terms of capabilities, we will ask, what are these messages that Alice picks as far as the attack games are concerned? And again, make a choice that is common in cryptography, but one has to get used to it, which is that in our definitions, the adversary picks them. And this is called a chosen plain text attack. The intent is to model that we would desire security even if the messages chosen are the most convenient from the point of view of the adversary towards breaking the scheme. Certainly one may argue that in real life it would be difficult for an adversary to actually pick the data Alice encrypts. That's actually true to some extent, but there are scenarios where the adversary can have quite a bit of influence. But in any case, it's again a case of being conservative. So now we get to the heart of the definition. And it may be worth pausing at this point to say that in some ways the course begins here. This is the first place we encounter a formal metric of security, and we go beyond stories and informalities towards mathematical definition. And a large part of the class is going to be about understanding and using these definitions. So we have to pay a lot of attention to what the language is and how these definitions are written, how they work, and what they mean. So let's try to go over it slowly. We have something called a game. The game has a name, TKR, which stands for Target Key Recovery. The subscript is a block cipher, or actually more generally, a family of functions. Remember that we have fixed this family of functions and it's public and known to anyone, and it parameterizes the game. That means the game is measuring security of that particular family of functions. what the game does is provide a set of procedures, some of which can be called by the adversary. It's like an API, application programmer interface. So the adversary has black box access to these procedures, and it can call them according to rules dictated by the game. And the game will eventually decide whether it thinks the adversary was successful or not. The first procedure is initialize, and what it does is it picks a key at random from the set keys. What is the set keys? The set of keys of the family of functions E, determined by E. Now, this plays the role of the target key. In our minds, we might be thinking about Alice and Bob as using this key, but the game doesn't explicitly talk of Alice and Bob. It will have encapsulated their capabilities into procedures in the game so that they don't appear in the abstraction. So that key is now fixed, but it's hidden. The adversary cannot get it back or see it. Or the game will just run this procedure, or the adversary can by calling it, and it'll be initialized and stuck there. The procedure the adversary can call is called FN. It stands for function. The adversary provides a message M. What is this message? Anything in the input space of the block cipher. Any input to the family of functions or block cipher. And once the adversary has provided that, the game processes it in the following way. It runs the block cipher, this fixed family of functions, on the hidden key from here and the message supplied by the adversary to get an output. And whatever that output is returned back to the adversary. So the adversary is able to get outputs but not see the key. What does this model? It models its access to the ciphertext on the wire. These are the ciphertext Alice creates and the adversary obtains by eavesdropping. But in our game, there's no Alice, no Bob, no eavesdropping. You just call this procedure, you give it an M, and you get back this result. The fact that the adversary chooses M represents our chosen message attack. We call this a query, and we call FN an oracle because it's something that the adversary only has black box access to. It can make as many queries as it wants. We will see that security will depend on them, but the adversary can go ahead and make queries as it wishes. After a while, it has collected a whole bunch of ciphertexts, and it knows their corresponding plaintext. At some point, it may say, okay, I'm ready. I'm ready to try to win the game. What does that mean? Well, I need to find out what K is. I need to determine it. So the adversary, in whatever way it wants, will come up with what it thinks this key is. And then it'll ask the game, did I get it right? It'll call this procedure finalize. Alternatively, it will simply halt with a certain output, and that finalized procedure is viewed as automatically called. That finalized procedure will take this adversary provided key and test whether or not it matches the target key over here. If it does, the game returns true, otherwise false. This is a Boolean. You evaluate the Boolean expression k equal k prime, you get back either true or false, and you return that Boolean. Whatever is returned there is called the output of the game. That's what finalize returns. What the game returns is what finalize returns. Okay, so hopefully now you understand how this game executes. It's set up here through initialize. Adversary calls this procedure to get the results, but it doesn't know the key. Then it creates its guess for the key, and the game checks if it's right or wrong. Now, how the adversary does all this, subject to the rules of the game, is up to it. We don't tell it what messages to call, it decides. We don't tell it how to find a key to provide here, it decides. There are many different adversary strategies, all doing different things, whatever they want. We're not concerned now with what those are, we're just concerned with determining what are the rules of the game, when is the adversary successful or not. Okay, so we know now when the adversary is successful is when the game returns true. However, there are probabilities involved. This key is chosen at random in particular, so whether the adversary succeeds or not becomes a random variable, and there's a certain probability the game will return true. We call that the adversary advantage. It's written like this. It's the probability of this event that the game TKR sub E executed with adversary A returns true. The game doesn't depend on the adversary, but the advantage does. It depends on the adversary, the family of functions, and this, which indicates the name of the metric and tells you what game you're talking about. And this is a number, and the bigger that number, the better the adversary does. Okay, so now this is something that will need revisiting. You may have to go back and, if you haven't seen things like this before, and see what it is again. And we will delve into these definitions quite a bit, trying to elucidate them and use them and do examples, and all that is good and coming. But before we do that, let's go on and complete our definitional story by also giving the second definition. The second definition relaxes the first one. So let's see how that happens. We first need a certain definition related to a key. Again, we fix our family of functions with its key space and domain and range. And we assume that we have a sequence of input-output examples. So you have message, ciphertext, message, ciphertext. You have Q such examples. Each example is a pair. These are just strings, or the first element is always from D, the second is always from R. We want to define what it means for a key K prime to be consistent with them. That is true if, when you evaluate this family of functions on the key K prime with input M1, the output is C1. Furthermore, if you evaluate it on input M2, you will get output C2, and so on. So you write down this sequence of inputs and outputs of the block cipher, and you then ask, does this key explain them? If you apply the family of functions to this input with this key, do you really get this output? If you do, the key is consistent with that list. So let's try an example. Here's a specific family of functions with 2-bit keys, 2-bit inputs, and 2-bit outputs. It's shown as usual with a table. So here are the possible inputs, here are the possible keys, and the output of E on this key and this input is this. The output of E on key 01 and input 01 is 10, and so forth. So we know how to read the table. Now consider this pair. This is a possible input 11 simply because it appears here. This is a possible output 01 simply because it's a 2-bit string. Think of it as this list, but a very compact one. The value of Q is only 1. It's a list of length 1. For this list of length 1, I look at a specific key 00 and I ask, is it consistent with that? How do I check that? I want to know if this input 11 maps to 01 under 00. Does it? Yes. That means this key is consistent with this. Take the same pair, again a list of length 1. Is key 10 consistent with this? To check, you look at this key, you see what this input maps to. It maps to 01, which is what's written here. So this key is also consistent with this. Okay, now we look at lists of length 2. Here the value of Q is 2, and we're asking whether a key is consistent with both of these input-output examples. So that would happen if, with this key, 0, 1 maps to 0, 0. Does it? Yes. But also 1, 1 maps to 0, 1. Does it? Yes. How about key 1, 1? Is it consistent with this list of length 2 of this input-output example and this one? That would happen if under key 1, 1, 0, 1 maps to 0, 0. It does. 1, 1 maps to 0, 1. And it does. Okay. We now have this concept of a key being consistent with some list of inputs and outputs. At a high level, we are going to introduce a new game and a new metric of security. It's still about a family of functions. It's still about finding a key, except that we're not seeking the target key. We're going to seek a key consistent with the inputs and outputs produced by the target key. So let's see what that means. We fix our family of functions and some adversary, and we change a little bit the way in which the interfaces work. Our new game is called KR. It's parameterized by this family of functions. It gives procedures whose names are the same as before. There's an initialize, an FN, and a finalize. The code is a little bit different, but the names are the same. What does initialize do? As before, it picks a key at random from the key space of the family of functions. That again is the target key, and we call it the target key as before. Internally, it also initializes a counter to 0. It will use that for its own purposes. As usual, the key is not exported. At this point, the adversary has no idea what the key is. Now, just as before, the adversary starts calling this procedure on any input M for the block cipher or family of functions that it wants. And what does it get back? The same thing it did before. There is no change from the adversary perspective to how this procedure behaves. The game evaluates the family of functions on the target key and the message provided by the adversary, which has simply been renamed here. And that ciphertext is returned. So why is there a difference in the way it's written? Simply that the game is doing a bit of bookkeeping. Every time it gets an input, it remembers it. It records it as the ith input, indexing a list inside the game so that it remembers it. Okay. Finally, again, the adversary has the same task as before. It trundles along and it outputs a certain key K prime. And it asks the game, did I win or not? And the game is going to tell it true or false. And this is where there's a change. Remember that earlier in our prior game, winning was simple. It was, does K prime equal K? Now it's more complicated. It lets the adversary win, certainly if K prime equals K, but it also lets it win more often. How is that? What it does is it says, consider the pairs M1, C1, M2, C2 created through FN, right? So the first time the adversary called, the message was M1, it got back C1. The next time it sent in M2, it got back C2. We look for the adversary key here to be consistent with those examples. As long as the adversary provides such a key, it wins. How does the game check this? I here is the current value of this counter. So it's the number of queries made to FN. You now walk through each of those queries, j equals 1 through I, and for each one, you evaluate the family of functions on the adversary provided key and the message that was recorded here to see if you obtain the ciphertext that was recorded here. If you do not, the adversary loses. You set win to false. If the adversary loses, if fails to have this match happen even once, it's going to lose. To win, it must be the case that all of these are equal and they all match up, and then it wins. Okay, More succinctly, the game returns true if the key provided by the adversary is consistent with this list M1C1 through MQCQ that was produced over here. Remember that this list is produced under the target key. It's not an arbitrary list. So you're saying we know that the key K is responsible for this list, but maybe some other key K prime might have produced it as well. And if so, by providing it, the adversary is still viewed as having won. Okay, that is the main part of the definition. And now there's this if condition. This if condition simply requires that adversaries are not allowed to repeat queries. They say that if the messages that the adversary provides are not all distinct, it can't win. Why do we do that? Well, first off, notice that there's really no loss of generality because the adversary has no incentive to repeat a message. If it repeats a message, it gets back exactly the same output as before, and it knows it will get that, and it hasn't learned anything. So no sensible adversary would actually repeat a message. But why would I outlaw it? Because it turns out that the number of queries to FN is an important parameter of security. And to make it meaningful, the queries need to be distinct. So we'll talk of a Q query adversary. And a Q query adversary to be different really from a Q-1 query adversary really requires that those queries are distinct. And so I simply want that to be part of the definition. Okay, so again, this is something that will, if you haven't seen it before, will take some looking at and understanding. But we will elucidate it a little bit more as we go on. And here's the first element of that. The claim here is that consistent key recovery is a relaxation of target key recovery in the sense that an adversary, the same adversary, can play either game. But when it does that, it's more likely to win the key recovery game than the target key recovery game. It's easier to violate key recovery than target key recovery. And indeed, that's kind of the point. Why is this true? Well, consider the consistent key recovery KR game, and suppose the adversary made certain queries to the Oracle FN and obtained certain ciphertext. Now, look at what possible keys the adversary wants to output. It wants to output something consistent with that sequence. What are its choices? Well, there's one choice that's very obvious, which is the target key. These examples were created under the target key. The target key definitely maps M1 to C1 under E and MQ to CQ and so forth. Why is that? Because you see that that's how the C's were produced from the M's. By definition, the target key is consistent with this list. So outputting the target key would definitely be a win in this game and in the TKR game too. But maybe there are other keys not equal to the target key that are consistent. And if so, there are more ways to win for the adversary. You've enlarged the set of things that allows it to win, and thereby you've made winning easier. Let's formalize that a little bit. Let E be any family of functions, and A be any adversary, but assume that its queries to this oracle are distinct. Now, given that these two games have the same oracle names and return the same types of things, we can run the adversary in either game. We can keep the adversary fixed, let it play the TKR game, and measure its advantage. We can keep it fixed and let it play the KR game and measure its advantage. And we would get back two numbers, possibly different ones. If we compare them, we would find that this one is always at least as big as this one. That is what the proposition says. Your chance of winning the KR game is at least as large as your chance of winning the target key recovery game. Why is that? Effectively due to this fact. Consider what key the adversary returns. there are two choices. Maybe it equals the target key, in which case it wins both games. Or it doesn't equal the target key, but it's consistent with the input-output examples, in which case it wins this, but not this. Whenever the adversary returns the target key, meaning whenever it wins this, it will certainly win this. And so this probability can only be greater than or equal to this one. Okay. So we have now established a way to measure security. And this gives us simply a metric. If you have an adversary, you could imagine running it in either of these games and computing a number that says how well the adversary does. The larger the number, the better it's doing. The smaller the number, the worse it's doing. But to see a specific example would consist of writing down some particular adversary and actually seeing how well it does. That's what assessing security actually comes down to. It's saying, are there adversaries that do well or not? How does the advantage grow as a function of adversary resources? So we have now a way to think about security, and we can actually start thinking about it. When we do that, we realize that there is an obvious and attack against any family of functions from the point of view of key recovery that we really cannot exclude. And that attack is simply to try every possible key until you get the right one. What makes that attack possible is that there's a finite set of keys. As long as the set of keys is finite, the adversary can just test them one by one until it finds the right one. And that's it. There's no way to prevent that. So let's take a closer look at that attack and what it means for security. Again, we fix the family of functions. It's public and known. And let's enumerate the space of keys. Let's say there are n keys, and we'll list them as T1 through Tn. Usually n is a power of 2. This is the set of strings of some length. For DES, n is 2 to the power 56, and this is all 56-bit strings. We'll also list the space of inputs as x1 through xd, where d is the size of the set, big D. And we will associate to the attack a parameter, which will be the number of queries to fn. That parameter cannot be bigger than the number of possible inputs. And we'll now design a specific adversary called E sub EKS for Exhaustive Key Search adversary. So this is our first explicit attack. An attack is represented by an adversary who will show up in pseudocode in this way. So since we're designing the attack, we get to say what it does. But we are playing a very specific game. Whether it's target or consistent key recovery doesn't matter that much because the interfaces are the same. Think for the moment it's target and we'll consider both, or think it's consistent key recovery. Doesn't matter. The adversary's job is to make a bunch of queries to fn. This is where we see how the game oracles or procedures get invoked. The game has already run initialize and created a target key k. That is not available to this adversary. It has no idea what that is. What it can do is it can call fn on messages of its choice and get back outputs. So it'll do that. And it does that, our specific adversary, quite simply. It just walks through the first queue of these inputs. As many as it's allowed, it runs through this procedure and it collects these input-output examples. Okay. But now it has to output its guess for what the key is, because it's trying to find the hidden target key. How is it going to do that? It's going to say, I'm just going to try all these keys one by one. So it will have a for loop going through all of these keys, and for every key, it will do a certain test. And if that test succeeds, it'll say, I think that's the right key, and I'm returning it. Okay. So the first time the test succeeds, it's done. That's the key it'll return. So what is the test? It's just that whatever examples it says here are explained by this key. How does it test that? Remember that the family of functions itself is public, and we can assume that there is code available publicly to compute it. The adversary uses that code here. It explicitly runs it or calls it as a subroutine. It runs it on inputs that it knows, the ith target key from this list and the jth message. And it sees if it gets back the same thing as here. Whenever it hits the target key, that should be true, and so it expects that at some point it will trigger. Okay. So again, cycle through all keys, do a simple test. Is that key the right key or not? If it looks like the right key, return it and halt. And otherwise, go to the next key in the list. Each test involves a computation of the family of functions or block cipher, not just one, but q of them, because there are q input-output examples. It's simplest usually to starting point to think that q is just one, but sometimes we like it to be a little larger. At this point, we have a specific and clear definition of an adversary in pseudocode. We also have our two games, consistent and target key recovery, and we can ask, relative to either of them, what is the advantage? What advantage does this particular adversary have? To determine that, we would go look at the game, and we would ask, what is the probability here that the adversary succeeded in making the game return true? That would mean that over here, it returns true. So then we look at the game. The game says that happens if the family of functions or block cipher applied to whatever the adversary returns to finalize, and to each message for which the FN was called, does result in the ciphertext that was created under the target key over here. So if we go back here, we can now try to assess that. So the analysis comes down to this, that the answer is very simple. The advantage of the adversary is 1. In other words, it always wins. It will always succeed in getting the game to say, yes, you won. Why is that? Because the target key itself has to be somewhere in this list. This list is a list of all keys. A priori, the adversary doesn't know where it is, but it's there somewhere. Let's say, for example, it's in position I. At some point, the adversary will hit that ith position. When it does so, we claim that these tests will all be true. Well, of course, because these, through this procedure, are created so that C sub j is E under the target key of M sub j. When T sub I is the target key, you have a tautology. Of course, they're the same thing. So at that point, of course, this will trigger to be true. So given that the target key is in the list and is, of course, consistent with the input-output examples, and the game is testing whether what the adversary returns is consistent with the input-output examples, whenever the adversary hits that target key, it is going to return something which will make the game say yes. Okay, now is it possible that it doesn't hit that target key? That could happen because it stops earlier in this loop. The reason it stops is that it found something else that worked and returned that. That's fine, because once it found something else that works, that other thing is meeting the definition of consistency and hence is also a win. So no matter what, you will keep trundling along. Either it has won already, or it gets to position I, and then for sure it wins. And so overall it has advantage 1. This is something worth going over slowly to make sure that it makes sense. Now, remember we had two metrics of security. We have so far assessed how well the adversary does, this specific adversary, exhaustive key search, relative to the metric of consistent key recovery. What about target key recovery? Does the adversary succeed in recovering the actual key that the game has chosen and used as the target? To do that, we would assess that. We would look at the definition of target key recovery. Under that, the adversary is getting back examples under the target key, and it wins if it outputs that key. Okay. So, well, we can certainly start by reasoning as before. We know that the target key is somewhere in the list. Say it's the ith key. So at some point, the adversary hits that, and then it outputs it. So that means it wins, right? But no, there's a catch here. The difficulty is that suppose the target key is, let's say, the mth key in the list. But suppose there's a prior key which is consistent with the input-output examples. There's no reason that shouldn't happen. Well, in that case, that key is the one returned because that will be encountered first in the for loop. And so, in fact, not the target key, but something else is returned. The consistent key recovery game would be quite happy with that. It likes that other key just as much as the target key. But the target key recovery game doesn't. It wants the actual target key, and this time it's going to be foiled. It's not going to get that. So if I ask what is the advantage of the adversary, I would have to try to assess, how likely is it that prior to hitting the target key in this list, I don't stop. I don't hit any consistent key different from the target key. So we can think about that question, and we understand that that's what influences the advantage we obtain. But the fact is, it's rather difficult in general to know how likely that is. For example, for DES, I don't know how often it happens. And as a result of that, we kind of have a hard time knowing what this advantage actually is. So I can't say look at a block cipher or family of functions like DES and say, oh, for exhaustive key search, the TKR advantage has the following value. I really don't know what it is. Okay, now looking at this is one of the reasons why, in fact, there are two metrics. It may have been difficult to motivate this earlier, but the reason for two metrics is exactly that while target key recovery is kind of more intuitive and what we want to consider, it's very hard to deal with. It's very hard to estimate. And so we tend to reason in terms of consistent key recovery. Consistent key recovery is kind of more fair. You can't expect the adversary to do better than find a key consistent with the input-output examples. So is there some way to reconcile them or to think about the gap between them? Well, heuristically, for most block ciphers of interest, we expect that when you run this exhaustive key search attack, your target key recovery advantage will in fact be close to 1. The reason that's true is because it's most likely the case that the target key is the only key consistent with the input-output examples. So there's no danger of ambiguity of finding a wrong key because it just doesn't exist. There's only one key consistent with those examples, and that's the target key. But for that to happen, you need sufficiently many examples. And an estimate says that number of examples has to be somewhat more than the ratio of key length to input length. For DES, that's 56 divided by 64, so Q equals 1 should hopefully be okay. For other block ciphers, you may need larger numbers. Now, it's important to understand that this statement here is a heuristic. It's not a theorem. It's not a formal statement. is just a kind of empirical feeling about what happens as reflected by the term real here in quotes. What is a real block cipher? Not something mathematically defined, but something like DES or AES, which is the kind of thing cryptanalysts usually design. In that case, we heuristically and empirically expect something like this to be true. And because of this, we think in practice that these metrics are going to be quite close to each other. Now, there will be a homework problem which goes into this more precisely. Okay, so understanding the difference between these things is worth a little bit more time. So let's think of the following kind of converse or contrast to the statement on the last slide. There we said that for practical or real block ciphers, we would usually imagine that the consistent and target key recovery advantages of an adversary are the same. But this exercise says it's not always true. And how does it do that? It says, show me a counterexample. In this exercise, you're given a key length and a block length, and then you're asked to design your own block cipher. So you specify the block cipher algorithm. But you do it in a perverse way such that the following things are true. It should be extremely easy to violate key recovery security in the consistent key recovery sense. And it should be extremely hard to violate target key recovery security. There's a big gap. How does that show up? The first statement says that for any number q less than the number of possible inputs of examples, we can design a Q query adversary. It makes Q queries to Fn. It has a quite small running time proportional to the number of queries, which is kind of inevitable, and the lengths of things involved. But its consistent key recovery advantage is 1. It's extremely successful. What happens with target key recovery? If you ask how well this adversary did for target key recovery, the answer is very poorly. Its probability of success is only 1 in 2 to the negative k. But in fact, even worse is the case. No adversary does well at target key recovery. Not just this one, but any adversary you design has only this very small chance of being successful at target key recovery, no matter how many queries it makes. Right? So this shows a big gap. Think of k as 128 or 256. This is way, way smaller than this. How does that mesh with the last slide? This block cipher is not a real one, not in the sense that this is not the kind of block cipher a cryptographer would design in practice and use for encryption. It's one created as a mathematical exercise to illustrate a difference between two definitions. Okay, so now we saw that exhaustive key search is extremely successful. If I take a family of functions or block cipher, the advantage under consistent key recovery that exhaustive key search succeeds is actually 1. And even for target key recovery, at least as if we have a good block cipher like DES, it would also be 1. But that's a violation of security. Your adversary has found the key. It can decrypt anything it wants. That does not sound like good news. Why are we looking at these block ciphers and imagining that we have obtained some security if we have a blatant, easily described attack which has an advantage as high as 1? The answer, remember, is that attack success isn't just a matter of the probability of recovering a key, but the computational effort to do so. Security is always about effort, and that means time and computing resources used. So we have to look at the exhaustive key search attack and say, how long does it take to run this? Is the running time practical or is it prohibitive? Well, that is going to depend on the block cipher. It will be different for different block ciphers. So we could look at it as an example for DES. Okay, so we now have to assess the running time of this specific exhaustive key search attack. It's an algorithm, and according to CSE 101 or 202, we can assess in big O notation, hopefully better here, its running time. And we see that we will use Q to be quite small. Let's say it's just 1 or 2. So we won't think of this as taking much time. We think of the time as being the for loop. So the cost is n times the time of this test. And then we see that the main component of the test is executing E, where E is the block cipher itself. In other words, how fast you can run E is how fast you can run exhaustive key search. The faster you can compute E, the faster you can do the search. That means an attacker is going to look for the fastest possible implementation of DES and use that inside its attack. We've already said that attackers are well equipped, highly motivated, and well funded, and ours is going to find not just the best code, but implemented in hardware. And you can do that. DES can be run at over a gigabit per second in hardware. Okay, that's a per second rate. At DES, plain text is 64 bits. So the result is that your chip can perform the rate divided by 64, which turns out to be about 25 billion DES computations per second. That's a ridiculously high number of DES computations per second, and that'll mean we can go through this key space very, very quickly. However, the key space is pretty big. There are 2 to the 56 possible keys. On the average, maybe you'll hit the key you want, the target key, about halfway through. So say you expect your adversary to perform about 2 to the 55 DES computations. How long is that going to take it? Well, it's 2 to the 55 divided by 25 billion, which is about 1.4 times 10 to the 9 seconds. But that turns out to be about 45 years. And so now we start seeing why security may be hoped for here. It's true that the attack in principle will recover their key, but it takes 45 years to do that. And that's not such a huge worry from a practical perspective. We can be changing keys maybe frequently or doing other things. So we look at that, and that's kind of our assessment of security. Now, there are a few caveats. DES does have a weakness called key complementation, which reduces the search time by 50%. So in fact, it's about 22.5 years. Still, that looks fairly prohibitive. And so maybe we'll start thinking, well, DES is looking pretty secure. But we want to be wary about those kinds of conclusions. And in particular, actually, we know that it's no longer a standard, so there must be some reason for it. So let's think about this a little more. The exhaustive key search attack is actually a very dumb attack. It never attempted to look inside DES, to look at how the S boxes work, to find and exploit any actual weakness in the design. It's just a generic way of attacking any block cipher or family of functions. It's a brute force attack. Try every possible key until you find the right one. So cryptanalysts, after DES was introduced, started thinking, what if there are actually weaknesses in the design that lead to better attacks? And so they put a lot of effort into doing that, into figuring out if there are such methods. And indeed, they did find some. Now, it's interesting that they found it, but it's also interesting that it was not easy to find, and the discoveries in the early 90s were quite some 15 years after DES was standardized. So it took a while to find these weaknesses. The first method was called differential cryptanalysis, and the next one called linear cryptanalysis. So what are they trying to do? Remember that the time to beat is the 2 to the 56 DES computations approximately taken by exhaustive key search. 2 to the 56 is the number of keys, and so that's the time roughly for exhaustive key search. And the question is, can you do better by exploiting internals of the design? And differential cryptanalysis did. It got it down to 2 to the 47. That means that the running time was 2 to the 47 instead of 2 to the 56, which is a fairly significant improvement. And linear cryptanalysis got it further down to 2 to the 44. Okay, that starts looking more serious from the point of view of its impact on DES. And at this point, we start thinking, okay, maybe we should be worried about retiring this algorithm or something like that. But it's not that easy to retire an algorithm that's widely deployed. And so implementers and users are fairly cautious and reluctant to do that unless it's really necessary. And they started pointing out at the time of these attacks that these attacks are not that easy to mount. And one reason was that, remember that in exhaustive key search or in any attack, there's this parameter Q, which is the number of input-output examples under the target key that you obtain. For exhaustive key search, it was just 1 or 2, and so it was an insignificant concern. These new attacks bumped that up to something close to the running time. You needed a massive number of these input-output pairs under the target key. And this was quite prohibitive. First of all, at least in the computing possibilities of the 90s, it would take over 200 terabytes to just store all that information. And that doesn't sound like a lot now, but it was back then. But secondly, you would have to be in a position where the real user was actually encrypting under the target key this huge amount of data. And they could easily stop before doing that or have no need to do that, and the attacks would become infeasible. So the result was that in practice, these attacks were viewed as prohibitively expensive. And so this was viewed as interesting theoretically, but not a break of DES. And so DES continued to be reaffirmed as a standard and continued to be used. All right. But as we know, it wasn't, in fact, continued much beyond that. So let's ask why. So let's go back to exhaustive key search. And I claim that when we analyzed its running time and how much time it took, we made a mistake, or at least we failed to account for something which makes a drastic difference. We said correctly that the running time is effectively the number of operations of DES you perform. Again, thinking of Q as just being 1, you have, let's say, 1 DES per iteration in the loop, so maybe around 2 to the 55 or 56 DES operations. And we can do them with hardware. What we fail to consider is that you can do them in parallel. Nothing prevents you from testing multiple keys at the same time because you have hardware available to do that. But this makes a big difference if you systematically exploit it. And in the early 90s, just around the time of these other attacks, Michael Wiener decided to architect a DES cracking machine. That means he didn't actually build it, but he designed the architecture that used special purpose hardware and had a whole slew of racks covered with chips, each with many, many DES processors, which was cranking through as many keys as possible at the same time and reducing the key search. And this machine was able to find the key in just 3.5 hours. So this is really a devastating change in our understanding of security. From years to hours would render this design completely insecure. When you're designing something like this, there's a question of what is the metric, and Wiener had an interesting answer to that. He took the metric to be the financial investment that the attacker might make and set it at $1 million. If you have more than $1 million, you could use more chips and get it down more. If you had less, buy less chips and the time would go up a bit. It's a fairly conservative estimate given what we've said about the capabilities of determined adversaries. But with this estimate, 3.5 hours to find the key. Once that was known, efforts started up to actually do something like this. It was realized that you can exploit parallelism in various ways. So, for example, there's a company called RSA which would publish something called DES challenges. They would pick a random target key and provide a ciphertext under that key of some plain text, publish the ciphertext, and give a reward for recovering the plain text. It looks a little different from key search because you have to recover the plain text rather than being provided it. But in practice, really the only thing you can do is run a key search attack, try to find the key, decrypt the ciphertext, and use that as a test. In other words, you would do exhaustive key search where your test for the correct key was whether the decryption of Y was kind of something that made sense as an English phrase. Okay, so they offered monetary rewards. The first finding there was that in 1997, a reward of $10,000 was claimed by a group that did a distributed computation. They didn't build hardware, they just farmed it out as a distributed computation over the internet and took a certain number of months. That was brought down quite a bit by later distributed computations. The Electronic Frontier Foundation eventually built a machine. They didn't invest as much as Wiener did, maybe $250,000, and it took them 56 hours. And this time kept coming down. And so you see this sort of very pragmatic demonstration of the insecurity of DES. So the summary of all this is that we have at a pragmatic level to declare DES to be broken once we see all this, because it's possible to find keys in practical amounts of resources. But we also see that the reason it happened is much less bad design than too short a key size. 56 bits was, by modern standards, too short a key size, resulting in too small a key space. If the key space had been bigger for a design that was equally small, maybe DES wouldn't today be broken. And indeed, it's interesting that DES had this type of strong structure. I remember I was at IBM at the time that differential cryptanalysis emerged. One of the designers of DES, Don Coppersmith, was working there, and he gave a little seminar where he explained how he had built already into the S boxes in the 70s defense against differential cryptanalysis. And he had anticipated the attacks that came in the 90s and built in enough defenses that those attacks, while they made a dent, didn't actually do too much damage. It was a visible way to see this was that DES wasn't the only block cipher around, and other block ciphers were collapsing under differential cryptanalysis, and DES was still standing up pretty well. They didn't anticipate linear cryptanalysis, though. But still, this was good evidence that DES was a strong design with weak choices of parameters. So it's interesting to look at how all this plays out in popular discussions on the internet. Here's a nice little article summarizing ways to break DES. It tells you about exhaustive key search, about these dedicated hardware machines. It discusses in more detail the Electronic Frontier Foundation effort and how they built Deep Crack, which cost about $200,000 and had 1,536 dedicated chips. And it checks about 92 billion keys per second. They compare that to the distributed net type approaches, which use clusters of computers and see how many keys they can check. They look into other kinds of aspects. They discuss differential and linear cryptanalysis and get more into their concrete complexity. We can also look at how people are doing in terms of DES cracking. You can now go to crack.sh and you can crack a DES key. So they've built this now with FPGAs and made it available, and they can exhaust the key sets in around 26 hours. And they're hoping that this will demonstrate the insecurity of DS and motivate people to adopt better standards. This is a kind of nice little story about the day DES died. It just tells the history of how it felt like to see those attacks and finally see that, okay, we really just have to give up about this. Okay, let's stop there.